Dear colleagues, my name is Alexander Ledkov. I am an associate professor of the theoretical mechanics department at Samara National Research University. My report is devoted to the problem of modeling the 3D motion of space Tether system, which is used for putting payload into orbit. The payload orbiting is one of the most important tasks of astronautics. Combining schemes using auxiliary space Tether system can reduce the cost of the payload lifting operations through the use of lighter rockets. In the framework of the scheme considered in the article, the payload is lifted to a low orbit by a light rocket. There it docks to the lower end of the space Tether system. Then the payload is raised by the system to a higher target orbit, where it undocks and continues its free orbital flight. As a result of the maneuver, the orbit of space Tether system is lowered, but this problem can be solved, for example, by using electrodynamic tethers. The tether spin-up after docking can be done using jet engines by changing the tether length due to the interaction of electrodynamic tether with the Earth's magnetic field, by using controlled movement of additional mass along the tether, and finally due to the interaction with the atmosphere. In the study, the latter method will be used. Let's look at the proposed scheme. The stabilized space Tether system moves in a circular orbit. A payload is lifted to a low orbit by a light rocket, and it docks to the model at lower end of the space Tether system. After that, the balloon inflates and envelops the docked payload. Since the balloon has a large cross-section area, the increased aerodynamic drag brings out the tether system from equilibrium state. As the system rotates, the aerodynamic drag decreases due to a decrease in the atmosphere density. Therefore, after passing through the position half p, the disappeared aerodynamic drag force will not try to rotate the tether in the opposite direction. After tether overturn, the payload undocks and the balloon deflates. I have conducted research of this scheme in a simplified planar statement, and now I want to do more accurate calculations in the 3D case. Thus, the aims of the work are to develop a 3D model of the system and to study the influence of balloon oscillation on the tether motion. A considered mechanical system consists of a satellite, a heavy elastic tether, and a balloon with a payload inside it. It is assumed that the satellite is a mass point and the balloon is a rigid body. The length of the tether is many times greater than the size of the balloon, so it can be approximately assumed that the system center of mass lies on the tether line. The figures show some points that will be used below. Before constructing the equations of motion, some reference frames should be introduced. Recalculation of vectors coordinates from the one coordinate system to another will be carried out using rotation matrices. Don't be afraid of this bulky drawing, we will clarify it. To transfer from an inertial reference frame to an orbital frame, we need to make two turns. The first one is rotation around z-axis. Here you can see the corresponding rotation matrix, and the second rotation is rotation around y-axis. I draw your attention that the second turn is made clockwise. Transfer to tether reference frame is carried out using two turns, again around the z-axis and the y-axis. The transition from the orbital to body reference frame is carried out by three turns around axis z, x and z. Lagrange equations of the second kind will be used to construct a mathematical model. The state of the system is described using 9 generalized coordinates. To determine the Lagrange function, the kinetic and potential energy of the system should be found. The kinetic energy is the sum of kinetic energy of the satellite, of the balloon, and of the tether. The potential energy of the system is combined from the potential energy of the satellite, the balloon, and the heavy tether in the Earth's gravitational field, and the potential energy of an elastically deformated tether. Here you can see the kinetic energy in matrix form. M are masses, R are position vectors, omega are angular velocity vector, and I are inertia tensor matrices. Here you can see matrix expressions for calculating position vectors of the system's points and their coordinates in various reference frames. The reference frame in which the coordinates of the vector are specified is indicated by the superscript. The absence of a superscript denotes the inertial coordinate system. The next slide shows the matrix of inertia tensors of the tether and the balloon. Also, here you can see the matrix expression to calculate the angular velocity vectors and their coordinates. Here you can see the potential energy of the satellite as a mass point in the gravitational field, the potential energy of the balloon as an energy of a rigid body in the gravitational field. To calculate the potential energy of the tether, we can find the potential energy of its elementary section and take the integral over the tether length. Here you can see the potential energy of an elastically deformated tether. Since the aerodynamic force acting on the balloon is not potential, the corresponding generalized forces must be calculated. We denote the center of pressure in which the resulting aerodynamic force is applied by the point K. For a special case of a spherical balloon, the resulting aerodynamic force is directed opposite to the velocity vector and its force is applied in the geometric center of the sphere. Substituting expressions for the energy and generalized forces in the Lagrange equations, we obtain a system of 9 differential equations of the second order. Using these equations, we carry out numerical simulation. As an example, consider the motion of a system with parameters and initial conditions given in the tables. We will carry out several calculations for various balloon center of mass positions. The position of the center of mass is determined by the parameter xc. The graph shows the dependence of the tether length deviations from the undeformed state. In all considered cases, the tether remains stretched. The time dependencies of the tether deflection angle phi3 and the balloon axis deflection angle phi5 in the orbit plane are shown on slide. In all considered cases, the tether turns around. Oscillations of the balloon occur near the tether. It can be seen that the most favorable situation is when the balloon's center of mass is shifted below the geometrical center of the sphere. Out-of-plane tether oscillations shown on this slide. It can be seen that their amplitude is small, although the balloon oscillates with a large amplitude. In conclusion, the following main results were obtained. A mathematical model that takes into account the effect of the aerodynamic force on the inflatable balloon was developed. It was shown that considered space tether system can be transferred from the stable radial position to rotation mode by aerodynamic forces, which act on the lower end of the tether. Oscillation of the balloon have a weak effect on the tether oscillations, and it was found that the most preferable situation is when the center of mass of the balloon is below its geometric center. Well, that's all I have to say. Thank you for listening. I'll be happy to answer your questions in comments.